Hey, hello, physics students. This is a little bit of a lesson on chapter 20, part one. Eventually, I think we'll have chapter 20, part two as well, where we'll talk about entropy. And because one of the statements of the second law of thermodynamics that we will see today is in terms of entropy, and it's really kind of poorly understood by the general population, and we kind of give words to describe it, but it really has a mathematical definition as long as we stick with something like that. And there's really no ambiguity and so forth here. But today I'm going to remind you of some of the stuff that has happened in the past few chapters, kind of start putting that together. And your textbook wants to really apply it to this idea of heat engines. And that's all well and good, but I'll try to be looking at maybe the bigger picture, because really laws are supposed to pertain to really everything in nature, not just heat engines. So there's this sort of application of the laws of thermodynamics being applied to really the heat engines, and so we can take a look at that. That's fine, but we'll try to look at some more general ideas as well. So let me kind of remind you of some of the things that we've kind of come up against so far, and how we're going to kind of use this here to describe this idea of a heat engine. So number one, heat, probably a definition that you want to memorize. That's a transfer of energy from one object to the other object. Now, in your reading, you really have three main ways that this is going to take place, right? There could be conduction, and this implies that two objects are in contact with each other. So, for example, if you have a pot of maybe just boiling water, and you get a fork or a spoon or something, and you put it in there, right? So you put this metal into this boiling water, and let's just assume that the metal starts off at just room temperature, and you put it into boiling water, which is about 100 degrees C. Now, the molecules in the water are moving very fast, right? Because, I kind of see number two here. Temperature is the measure of the average kinetic energy of the individual molecules. So kinetic energy implies some sort of speed. So they're moving fast. They hit the fork or the spoon, they hit this metal, and they have collisions, right, with the atoms there. So they make the atoms in the spoon start moving faster. And so then the spoon starts getting hot. And that's what we mean by really conduction, right? That the two materials are in contact with each other. And then eventually, the product engineers, may want to put some sort of handle, on that spoon if it's going into, a pot of, soup or something like that, so that a human being can grab it, because eventually, everything is going to go to the same temperature. So as long as that kind of keeps boiling, eventually that spoon is going to go to that same temperature. So you might want to have some sort of wood or plastic handle or something like that. So there's some insulating material that does not conduct the heat very well through. Okay, so two definitions here, pretty important. So heat is this transfer of energy from one object to the other object. Heat can also move, you find out in your reading, through convection, where on average, when something gets hot, say a gas, the hotter molecules rise up, right? Heat rises. And you can kind of see this, sometimes on a hot day in the summertime, when you have the sun in the right place and you have the road in front of you, and you can sort of see the heat mirage coming up, off of, the roadway. And that hot air is kind of rising. You go, well, why does it rise? Well, the molecules in the air are moving faster. Therefore, the volume of that gas sample is bigger. And density is mass divided by volume. So the volume gets big, the density goes down, and hot things rise. And this is one reason why, we have these quote unquote hot air balloons, right? Get the air hot, and it becomes less dense. And then you can also have heat transfer through radiation. And typically that is electromagnetic radiation, or another way of saying that is light. And light is something that you will discuss a little bit in Physics 103. That is how the picture of the electromagnetic wave kind of comes about. But the properties of light, we'll look at this semester. And properties of light are, very well known, very well studied. And light is not really something that has mass, but it can do work on things that have mass. So it can push things around, and it has the easiest time pushing things around that have charge. So things like electrons and protons. And so when light from the sun comes and hits something, it can make the molecules in that something start moving around faster, and so it can heat that up. And that's what we mean by radiation. So sometimes the wavelengths of light will go through a material. A material could be transparent to certain wavelengths, and glass is like that. So we've got certain wavelengths that come from our sun, and you and I see certain wavelengths about 400 to about 700 nanometers. We call that visible light. And so we make glass, which is transparent to those wavelengths of light. They transfer through that. And so when they come into your car, those wavelengths can be absorbed by the upholstery and the dash and materials inside of there. And then those materials get hot, and they start, their molecules move around and heat up the air inside of the car. And so energy just kind of keeps coming into the car through the transparent windows, and that's through radiation. And eventually that radiation is absorbed by materials, and that's in contact with the air. And through conduction, you can heat up a car. So on a 100-degree day, it's pretty easy to get a car up to 150 degrees inside there and so forth. So there are these three processes. So make sure you pick those up in your reading and so forth, and you kind of have an understanding of that. And then sometimes the kind of the exciting one is this idea of conduction. And a lot of times I'll get a big block of ice, and I'll put steam on one side of a piece of glass, and I'll put ice on the other, and we'll melt a bunch of the ice and come up with some sort of thermal conductivity of that piece of glass. And this goes into what's in your house. Somewhere up in the attic, you should have some sort of insulation. So good thermal conductors have properties that sometimes you want, sometimes you don't want them to conduct. And so then you've got insulators, which have poor thermal conductivities. And so the material, in your attic is supposed to not allow the heat to transfer through it, very easily and so forth. So yeah, make sure you pick some of that up in your reading and so forth here. Internal energy. So we kind of went to great lengths in chapter 18 to really show, just kind of one thing that happened to be true, that the total energy of the molecules within an object is proportional to the temperature. And a couple ways of writing that. We can write that in terms of capital N or little n. Capital N, big number, that's the number of molecules. Little n, the number of moles. And so the temperature is directly proportional to the object's internal energy. And in this case, it's typically a gas. So you heat up a gas and you increase its temperature, those molecules now can do work. They can do serious work. They can really make things move and so forth. And this is, since they can expand so readily, this is really what you want, because right, work is force times a distance. You really want to displace something. So something like a block of aluminum, you get it hot, it barely moves, right? In the laboratory, you could barely see this substance move. Even though it did move, a micrometer can pick up maybe a millimeter or two of motion, but you're not going to get a lot of displacement. You want work, or force times this displacement. Gases are really what you're going to be going after and so forth there. So, so we want to kind of keep all of this right here so far in mind. Okay, next big idea. If heat is a form of energy, it ought to be possible to equate it to other forms. The experiment below found the mechanical equivalent of heat by using the falling weight to heat the water. This is the Joule experiment taking place around 1850. And so there's a huge migration of people from the East Coast in America to the West Coast because gold is found in California. And different companies are trying to build better steam engines, and they're trying to get the railroad line in place and so forth. And James Prescott Joule is working on the first principles of really how do you make better engines and so forth. And what he's really kind of doing here, he's just getting a weight. So you can see the weight here, and as it falls, so if you're thinking in terms of Physics 101 terminology, that weight has potential energy. It's off the ground, it's got mass, it's in this gravity field, and you let it fall, but it's tied by this rope, so there's some tension on it, and that rope is around the spindle, and then the spindle moves these little paddle wheels in this canister that's just maybe filled with water. Okay, so you lose potential energy, and as this object falls, and it turns into rotational kinetic energy of this, these little paddle wheels, but that gets the water moving faster, and the faster it moves, the higher temperature it's got. So he can see that he loses mgh, but he can, through very, very careful measurement, show that that goes directly into the temperature. And so this is really the great seminal experiment where people, and really James Prescott Joule is given a lot of the credit for showing that in a closed system, energy is conserved. That's really our great first law of thermodynamics. Now, in Physics 101, you have potential energies turning into kinetic energies. Or somebody has a ball and they throw it, kinetic energy, and it turns into potential energy. Maybe you stored energy in an elastic material. You stretch a spring and you let go, and it can make something move as it springs back. And then you could lose energy to forms like friction. So you really probably had about 4 accounts where energy can go. It can go into motion, kinetic energy. It can go into position in a field, and that wasn't a gravity field, that was gravitational potential energy. Eventually in Physics 103, it could be stored in an electric field or a magnetic field too. And then it could be stored in elastic materials, rubber bands, elastic materials, springs, and things like that. And then lastly, you had friction, maybe you're ripping you off. But it still could be accounted for, because the work of friction is just the force of friction times the distance that friction acts over. Now what we've got in this course is that energy can go someplace else, and it can go into this thing called temperature. That is really, it's really the kinetic energy of all the molecules. But since you have a huge conglomeration of molecules in a gas sample or a block of metal or whatever it happens to be, you really can't get in there and measure all of them. And say you just stick a thermometer in there. And through the work done in chapter 18, you see that the temperature is proportional to the average kinetic energy of these molecules here, typically. And it's really the Joule experiment here of a weight falling down, moving a paddle wheel, changing the temperature of the water in such a way that he can see that nature was keeping track of something. And so we really had, some physics at that time. You really had Newton's laws of motion. You had Newton's law of gravity. There is a lot of work being done in the 1800s on gases, pressures, volumes, temperatures, these types of things. A lot of work in the 1800s on electricity and magnetic phenomena, but there really wasn't this one law that kind of said that here's how nature is really kind of working at the bottom level, and this is where we start getting the conservation laws. I think Newton probably has a pretty good idea of momentum being conserved if there's no net forces on a system that is linear momentum, and later on, as people start looking at rotating objects, if there's no net torques on those objects, then the rotational kinetic energy is going to be conserved as well. Along with the conservation of energy, you can just about predict the motion of any object really in the universe, because nature kind of plays this game of these conservation laws. And that's really found here through this Joule experiment, but in general, I typically call this the first law of thermodynamics. And even though your textbook may be writing that right now in terms of engines and temperatures and so forth, it's just really true in general. Okay, let's kind of move on here. Now, the thermodynamic processes, we've seen this in a previous lecture, but it's kind of worthwhile to kind of go through these again, because we're going to start applying these here eventually to a heat engine. And if we have constant pressure, constant is ISO, and then pressure is baric, like a barometer. And our general definition of work is an integral of P times dV. But if the pressure is constant, it comes out of the integral sign, and we're left with a simpler version where we can just multiply numbers and not really worry about integration and so forth. So isobaric processes is one of our thermodynamic processes. We have iso there volumetric, and in these cases, work done by the gas or on the gas is zero, and you should really kind of know why that happens to be the case. Constant temperature, constant iso temperature, thermal, isothermal. We did a bit of mathematics, and on an isotherm, you kind of get something that looks like a slide on your PV diagrams, and that curve could be an adiabatic process, or it could be an isotherm. They kind of look the same, so somebody really kind of needs to tell you really what's taking place here. But the area underneath that curve is something that we're able to work out here, where it's nRT, natural log of the ratio of the final initial volumes. And then we have an adiabatic system where no heat enters or leaves the system, and that really implies that Q equals 0. And so the internal energy of the gas is just whatever work happens to be done. So remember the first law, that is the conservation of energy, says the internal energy, or the change of internal energy of the gas, is the heat that you put in, Q, subtract out what work you get out of the gas, and whatever is left over is still locked up in the gas. How's it locked up? In terms of temperature. So you get it hot, it expands, it makes something move, you get some work out of it, and the difference is still accountable. But if Q is 0, then what you're really left with is the internal energy. The change of internal energy is somehow proportional to that work, and the signs in front of work are important, right? So you want to make sure that you're always looking at the preposition. Is it by the gas or on the gas? If it's by the gas, right, that's a positive W. It did work. If it's work on the gas, you've got to put in a minus sign, and then we have a minus sign right there, and then those two minuses become a plus, and so the internal energy of the gas becomes bigger if you do work on the gas. Okay, so those are our 4 processes here. Now, let's take a look at something new here, and that's this idea of the second law of thermodynamics. And not surprisingly, that when you've got people working on electrical phenomena in the 1800s, magnetic phenomena, optical phenomena, heat processes, right? Suddenly there's just a lot of experimentation being done in all these different arenas and so forth, that there's going to be a number of statements being made that people are coming up with in their experiments. And it's not really clear, but they really all describe the same universe. That is, they really all imply the same things. And so I'm going to take a look here at a number of different ways of stating the second law of thermodynamics. And a lot of times they don't sound anything alike, but it's going to take the work of theory people to really look at different statements and kind of show, kind of behind the scenes that they really do describe, the same universe, and they really have the same consequences and so forth. Your textbook at this point is going to really kind of focus on one aspect or one statement of the second law of thermodynamics. And that'll probably be in terms of the idea of entropy. And I think that'll be our second lecture on chapter 20. I'll talk about entropy and show you how to do some little calculations with it and stuff, so you can start getting a better feel of what that definition really means, and how the second law really kind of can be written in terms of this idea of entropy. Okay, now the important thing here is that the second law really establishes what may or may not occur in nature. So some things are just not possible. A ball rolling uphill on its own is not possible, not when there's a net force of gravitation down on it. So unless you push the ball up the hill, it's certainly not going to do that. We just don't see those things happening. Something like a calculator. You imagine what it took for some company, in this case Hewlett-Packard, to make this, right? So there's plastics here, right? So maybe you've got some sort of polymer material. There's a liquid crystal display here. All the little keys have got capacitors. There is batteries in here that put charge in the capacitors, and when you push the button, then the capacitor releases the charge, and the little chips inside there are looking at charge, and they know which key that you happen to push and so forth. Somebody had to be able to program it, so you've got not only just physical components, there's just a lot of stuff here. I don't think we'd ever find something like this in nature, just kind of made on its own. Because it takes work to do that, right? You have to organize the materials, you have to organize the program and everything, and you can get more organization in nature only though if you have enough energy kind of coming in. So there's just going to be some things that just really we're not going to find happening in nature. And so a lot of ways to state the second law. So it works for every process known to us, not just heat engines. And so let's take a look here. Statement number one of the second law of thermodynamics: all natural processes tend toward a lower energy state unless work is performed on the system. I typically like that statement of the second law because it really applies now to just about everything, right? Why does the ball go down the hill? Well, that must be a lower energy state. And so it's losing potential energy. And so that's what it's doing. Unless you perform work on the system, and that means pushing the ball up the hill. And so when you walk into a room, you're not really worried that all the air in the room is locked up in a little corner up in the corner. You walk and all of a sudden you can't breathe. Well, that would take work to get the air and to put it in that spot, right? So it's just not part of our thinking at all, because we've never seen processes, really kind of do that unless you're doing a lot of work on the system and so forth. Okay, now it comes to heat engines. Statement B: no cyclic process is possible whose only result is to transform an amount of heat at a single temperature totally into work. Okay. We will be taking a look at some of these cycles. In fact, we've already done that in one lecture, where you've had these PV diagrams, and you've got the gas kind of moving through some of the different processes. And if you start somewhere on those graphs and you end in that same place, then that implies that it's a cycle, right? You're going through some kind of cycle. You start someplace and you get back to the same spot. No cycle process is possible whose only result is to transform an amount of heat. So you put some heat into the gas, that's Q. So you put 1,000 joules. You cannot get all of the 1,000 joules turned totally into work. Now, if you looked at it in terms of, statement A, and we're thinking about a ball rolling down a hill, can you get the ball and put it on top of the hill, have it roll down, get all of that work back. You go, well, I hear it rolling down the hill. So some of the energy went into sound waves. Probably the rubbing of the ball and the hill, that whatever that material is, there's probably a little bit of interaction there. So things probably heat up. There's probably a little bit less of friction. The ball is actually plowing its way through air molecules and it's displacing them. So it's fighting air resistance too. So if you lift that ball up, do you get it all out in terms of useful work? Well, no, right? Some goes to heating up materials and moving air molecules. Some of it goes into sound waves. So, it might take you 10 joules to pick that ball up and put it on top of the hill, but you're not going to get 10 joules out, right? Some of it's going to go other places. This other statement is kind of the same thing. You can't put energy into a gas and expect all of it to come back to you. Right. So as you move a piston, that piston is trapping the gas in there. It's got to be tight, right? So that the gas can't escape out the sides of the piston. So as it moves through the cylinder, there's probably a little bit of friction with that. Probably some of the heat bleeds through the cylinder and through the piston itself, and it goes into not your engine, not into the motion you're trying to describe and so forth. So you're never going to get everything that you put in back in terms of work. That would almost imply that you've got, almost like a perfect machine here or something like that. And there are some things in nature that it's just not going to allow. And so some people look at this, and your textbook will talk about this, that the first law kind of says you can't get something for nothing. That is, you got to put energy in and you can get energy out. The second law says you can't even break even, right? You put in 1,000 joules, you won't get 1,000 joules of work back because there's interactions between two objects. When two objects interact, they put forces on each other, and that means their molecules start vibrating and so forth when they hit and they smack into each other. And those are probably forms of motion that you probably don't want, right? That's probably not useful work to you, having vibrations of these molecules and so forth. A perpetual motion machine is not possible. People don't like this. People don't like to be told something is not possible, but this is essentially the same thing as letter B, right? If you put in 1,000 joules of energy, you're not going to get 1,000 joules of work. A perpetual motion machine is a machine that you put some energy in and it just kind of goes and goes and goes and goes. I haven't had one in a while. I used to always kind of tell this story. I used to be able to have people from just the region here call me up and say, you physicists don't know what you're talking about, perpetual motion machines. I built one. So yeah, I'd like to certainly see that, right? And they show up, and I used to see like maybe 1 or 2 a year. It's been a few years since I've seen one. But a lot of them are kind of along the same lines. They show up with something in the back of their pickup, and they get like a pendulum swinging, and then the pendulum just swings and it swings and it swings and it swings and it swings, and they go, aha, right, here's a machine, and it just kind of keeps on going and keeps on going and keeps on going. And this is no different than the observatory tower there at MJC, and you look at the tower, and there's a giant Foucault pendulum in there, and it just swings and it just never stops. And yet that big, massive 200-pound weight at the bottom that is swinging, it's plowing into air molecules. Air molecules should be slowing that thing down, and yet it keeps going forever. And the reason it keeps going forever is because it's being kicked by a little motor up on top, and that overcomes the air friction just enough so that the amplitude of the motion is always the same. And so when a guy's got this thing going in the back of his pickup, and I'll say, well, it's running into air molecules, and so that should be slowing it down. So where do you got this thing plugged in? He's, well, I got a battery right here. And I go, okay. And what happens when the battery runs out? He says, well, then I recharge it. I go, well, that's not a perpetual motion machine, right? You just put a bunch of energy into the system every time you have to charge the battery. And so, if you go in space and you just get an object, and maybe my writing pen, and you throw it, Newton's first law says that this object will move at constant velocity, straight line, constant speed forever. But if you want it to do work, it has to move another object, which means it has to have that interaction. And the minute it does that, it's going to lose some of that speed, right? It's going to slow down and so forth. So you can't sort of get it all in terms of energy back or anything like that at all. Okay. Another statement of the second law: heat will flow spontaneously from hot to cold, but not from cold to hot. Okay, now you kind of already know this, but now it's being formalized in the statement, that we're calling the second law of thermodynamics. So if you have two objects, an ice cube and say some boiling water, the heat it says will flow from hot, the boiling water, to cold. So if you put the ice cube in the hot material, what happens is that, about the hot water, its molecules are moving pretty fast. They hit the ice cube and they hit them pretty fast. They're pretty energetic, and they start moving those faster and faster and faster. And eventually your ice cube melts, right? And the whole thing goes to a little bit lower temperature than what you started with. So you have some mixture type issues that you dealt with in chapter 19 and so forth. Now, what we don't see is you put the ice cube in the boiling water, and the ice cube starts taking energy out of the very energetic molecules and slows them down. And really where you've got the heat going from the cold to the hot, right? We just never see that the ice cube gets sort of bigger and something like that. And suddenly takes all the heat out of that system. So it kind of goes one way, right? The ball rolls down the hill on its own. It never rolls up the hill on its own. And so we can basically say that statement here, but in terms of temperatures, which way do the temperatures go? And so when you kind of think about something hot and the molecules moving fast, hitting something where they're not moving very fast, the minute it hits something that's not moving very fast, it goes faster, it heats up. And so that's just the way it's going to always really be working here. So always try to be giving yourself some sort of just everyday analogy of really what these statements really kind of mean here. Natural processes, statement E, will tend to a greater amount of disorganization, that is, entropy will naturally increase. In our next lecture, we will look at entropy in terms of its mathematical definition and how you work with that. And this is probably the best way of looking at the second law and having mathematics put to it. And so this is really not a bad way of doing it. What I don't like is this idea of disorganization. I even see physics majors, kind of misusing this term and so forth. Entropy is a very, very precise definition here. But what I was kind of getting to before is that, when you put something like this together, this is an incredibly amount of organized material here in terms of the materials and the programming and everything that's going on here. And so typically something like this would not happen naturally, right? Your physics textbook, we would not just find that thing in nature, right? You can put a lot of work into a system, but probably naturally it's not going to just sort of take place because we have energy coming in from the sun just all the time. It's been happening for billions of years here on Earth, and yet there's no physics textbooks that are just sort of lying around or hanging from a tree or anything like that at all, right? It takes more than that to actually organize that material and so forth. And so this idea of organization is really best left to, I think, the mathematics, and that's what this entropy will really kind of talk about. It's going to be a pretty simple concept. It's going to be how much energy you've got per degree temperature, and you'll kind of see that it's really a concept that we need, and we don't have it yet, but it really will be needed here mathematically. So we'll take a look at that here. Okay. So different statements, as you're kind of always kind of in the back of your mind preparing, for next exams and so forth. Yeah, I would know, quite a few different statements of the second law, being able to describe those and things like that, right? That's always important to know your laws, know your definitions, and then we have to also be able to put those into play with some mathematics and stuff like that. Okay, now, heat engines. So now a heat engine is for us going to be kind of a theoretical process. It's not really one where we have to worry about flywheels and gear ratios and anything like that here at all. So a heat engine is going to be really a gas that we put energy in. We're going to get some work out, and there's something left over. There has to be something left over. Otherwise, we are defying the second law of thermodynamics. Letter B, no cyclic process is possible whose only result is to transform an amount of heat totally into work at a single temperature. Okay, so for us, a heat engine is going to be a device that converts thermal, that is heat energy, into useful forms such as mechanical and electrical. And so, this is how, if you live in Modesto, probably how you're getting your electricity. We have electrical energy coming, but we're not using thermal forms for that, but we'd probably call it some sort of, electrical converter, but you're really using potential energy, right? As snow lands in the Sierras, 8, 9, 10,000 feet, and it melts, it runs downhill, goes into the dams, and we store it. I think Lake Don Pedro is probably 6, 7, 800 feet deep or something like that, and you let it out the bottom, and so you have all that potential energy, and as it comes shooting out, because all that weight's on top of it, right? It turns some sort of wheel. And so you're once again kind of the Joule experiment, except we're using electromagnetic induction to be getting electrical energy. But we could be using the thermal forms to be doing that too, and so forth. So there's a lot of different ways to kind of look at this, but this is really our simple idea of what a heat engine is. So here's what we do. Heat's absorbed from a high temperature, so you got to get something hot, right? So in your car, this is you exploding gasoline or diesel, because there's some fuel injector, and this is kind of going by your spark plugs, which then ignites, the fumes, and you've got now a gas at very high temperature. Work is done by the engine. The gas gets hot, it moves the piston up, right? In the cylinder. So work is done. Heat is expelled by the engine to a source at a lower temperature. What does this mean? It means you got exhaust. So even though the gas expands and maybe it turns some crankshafts and eventually flywheels and your wheels are going down the road, not all of that work that you put in is coming back to you in terms of, all the energy that you put in is coming back to you in terms of useful work. So you're heating up the engine block. You've got to dispel some of that, in the radiator and so forth. The gas still has temperature, right? You're not sucking that gas all the way down to 0 degrees, all into useful work. So there's still a bunch of temperature left in that gas, and that goes out your exhaust. So there's still some sort of expelling at a much lower temperature than the hot temperature that you've got. And the hotter you can get it, and the least that you can throw out the back, the better it is for in terms of useful work and so forth. But you can only get things so hot. Eventually you start melting. Engines, you can catch on fire and different things like this. So you get to watch all your materials and things too. Okay, now in terms of a picture, it's pretty simple the way I kind of think about this here. You've got a heat reservoir. Doesn't matter what it's getting hot, right? It could be a nuclear reactor. It could be exploding gasoline. Doesn't matter. And in terms of your textbook, we're going to call that Q, right? This is energy going into the system. Q hot. Right? This is your hot temperature. Goes to the engine. We don't care what the mechanism really is. We get some work out. Okay, work performed by the gas, and then there's something left over still in that gas. The gas doesn't go away. There's still the sample, and then you kind of throw it out the back. All right, you throw it out the back exhaust. There's still some temperature there. Okay, so there's some exhaust, and there's still some heat there, but it's called cold, Q cold, because it's lesser than what you had just a few moments before you pulled a bunch of work out of that gas. And so the gas is really kind of like this magical step, right? Get it hot, does some work. There's still some temperature there, get it out of the way, inject some new gas, get it hot, let it do some work, get rid of it. And so you've got this kind of cycle. So your engine is just kind of cycling and so forth. Now, one of the people who's going to do a whole bunch of pioneering work here is going to be Sadi Carnot. And a lot of his work is at a very high level, much higher level than our textbook goods when it comes to thermodynamics and so forth. But his results is something that we can really kind of take to the bank, and that's going to be really the important thing here. But here is, the simple idea of what the heat engine really is kind of doing here. Okay, put some high temperature in, get some work out, but there is still something left over, right? And so really what you're paying attention to is really three things. How much energy did you put in? How much work is done by the gas? And what's kind of left over, right? Those are really kind of the three ingredients that are going to be pretty important here. Okay, how efficient is the engine? This probably makes sense here to you. Efficiency is the work done by the gas, right? That arrow kind of going up to the right there, divided by the heat that you put in. So you put in 1,000 joules, and let's say you get 600 joules of work out. Well, 600 divided by 1,000 is 0.6. That's a 60% efficient engine. Okay. Now, the work done by the gas, it probably makes sense to you, is going to be written as the difference between the energy that you put in and the energy that gets expelled. That is, if it's a good engine, it's using that difference as work. Okay, so right now we're not worried about inefficiencies really with friction and those types of things. It's all kind of thrown in here, all at one one fell swoop. The heat that you input is this Q hot right there. Okay, now let's get rid of that. Okay, now if you get Q hot divided by Q hot, that's just a 1. And so this ratio right here starts off at 1, but then you subtract off Q cold divided by Q hot. And the second law of thermodynamics says that Q cold cannot ever be 0. Okay, so you can't have a 100% efficient machine. The piston is moving, and it's moving in our atmosphere. The atmosphere is in the way, and it's displacing those molecules. Some work is done that you're not getting out, but it's also overcoming friction and all these things like that. So Q cold can never be 0. That's the statement up here, right? You can't have some sort of cyclic process where everything goes totally into work. There's always something sort of left over here. And that's Q cold. Now you can try to get that as low as possible, try to get Q hot as high as possible, and that's really kind of what you want to do for high efficiency. Now, there is a very, very nice argument in your textbook from the work of Sadi Carnot, and eventually we'll take a look here in a moment at the Carnot cycle, which turns out to be the most efficient engine that we can have. And we know from chapter 19 that gases have this smaller specific heat, that is Q equals something, right? You put energy in, and what it does, it changes the temperature of the gas. And so in the back of your mind, Q of a gas, it has some different ways it can kind of go here, right? But you really kind of have like N, you kind of have like a CV delta T, and we also had another process where it could have been a different constant if it was kept under constant pressure or constant volume and so forth. But the important thing here is that Q is proportional to the temperature. Q is proportional to the temperature. And so there's this actually very beautiful argument in your textbook. And a lot of times in lecture, I'll go through it step for step for step. We'll look at the Carnot cycle, and it usually takes about an hour to go through each step. And you end up with efficiency equaling something else than what we've got right here. But I think you can see very quickly that Q's are proportional to T's. no matter how you really look at the gas. And so in other words, those Q's eventually could be taken out of this efficiency definition and temperatures can be put in. After all, if you are an engineer working for Ford in Detroit, measuring energies is difficult. Measuring temperatures is simple. Temperatures are always much simpler. We just have better devices that can do that. Measuring how much work you really get out of something. Those aren't as easy measurements and so forth. So temperatures are really kind of nice here. But I would memorize here the definition of efficiency and how that turns into 1 minus Q cold over Q hot. Right, so there's nothing very sophisticated going on here really at all. Now, before we get to the Carnot cycle, we got to bring up a little bit of definitions here with this idea of reversible and irreversible processes. A reversible process, by definition here, is one that is carried out infinitely slowly. All right, this already tells you that this is not realistic, right? This is sort of your theoretical best that you can do. Infinitely slowly, so the process can be considered as a series of equilibrium states, and the whole process can be done in reverse with no change in the amount of work. In other words, you can put the ball up on the hill, never run into any air molecules, or if you do, you could put the air molecules exactly back in the same place. And as the ball rolls down the hill, any sort of work that is doing, right, you can do this infinitely slowly, so you can always kind of force everything back to where it was and so forth. And so these reversible processes really aren't realistic. They're kind of a theoretical best limit, really, is the way to think about them. And really, everyday terms, everything is really irreversible. When you roll the ball down the hill, maybe it's a ramp or something like that, you vibrate some of the molecules in the ramp, and you can't sort of undo that or get that energy really kind of back, or maybe put them exactly back where they were. The ball rolling down the hill plows through some air molecules. You can't really kind of put those all things back and so forth. That's really, real processes are irreversible. Once you roll the ball down the hill, you move air molecules out of the way. You're never going to get those back exactly where they were, right? If you could, that would be a reversible process, but you can't. So real processes are irreversible. All real processes are irreversible. Any thermodynamic process affects the environment in some fashion. Your engine is hot. You can put your hand on the hood after you've driven around for a while. You can feel it's warm. You are affecting the air around the engine, right? That means that the efficiency of the engine is not 100%, right? You're heating other things up that are not going into work. The engine gets hot. Things are moving. There's friction. All of that goes into this efficiency. Okay, so the efficiency is not 100%. It's not even close to 100%. Most typical engines are probably 15 to 20% efficient, something like that. Most of the work that you put in goes into something else. Okay, with your car, a lot of it's probably going into plowing out, through the air molecules and so forth. So there's a lot of air friction and all friction in the parts, and all the parts kind of get hot and so forth. So we have this theoretical limiting process called a reversible process, but really the real stuff are irreversible processes. Now, Sadi Carnot, so this is a French name, he finds out that the most efficient design is one that is cyclic. And you go, okay, what do you mean? What is cyclic? When you're looking at a gas process, that's one of these guys that I've already introduced you to, one of these PV diagrams. So the gas is somewhere on that graph. It's at a certain pressure, it's at a certain volume. Then you add heat to it, you get it hot, and it does something, right? So it probably expands, right? You want this thing to expand. So once it expands and goes this way, you got work out, okay? Now, what you got to do is have your mechanism, your engine, if it's really an engine, it keeps doing the same thing over and over and over again, right? It's not just sort of a one-off, right? Where you just sort of push something one time and then that's it. Well, that's not really what we consider an engine. An engine is something that just keeps doing the same thing over and over and over again. So eventually, somehow, you've got to get back to where you started, right? And that entails some sort of cycle, right? So you're going to go around some sort of cycle here if you want an efficient design. And that probably makes sense to you, right? Otherwise, your machine is doing something different every time. You have to design it differently every time. So it does something, you've got some work, and now you're going to go design something new, and it's going to do work in a different way. No, you want to, it gets designed once and just kind of keeps doing the same thing over and over and over again. A heat engine operating a reversible process between two heat reservoirs is the most efficient, right? This is your theoretical best that you can get, a reversible process, but that's not realistic, right? That'll never be reality. You can work towards that, but you'll never get that, right? That's having the ball roll down the hill, and it never affects the environment. It's always going to be affecting the environment somehow, some way, and so forth. So this is our theoretical best that we can do. Theorem number one: no heat engine operating between two heat reservoirs. The two heat reservoirs is Q hot and Q cold. Get something hot, and then there's something left over. You want the hot to be as hot as possible. You want the cold to be as cold as possible, because the work that you get out was the difference between those two. And that's really kind of what you want here. So no heat engine operating between two heat reservoirs can be more efficient than the Carnot engine operating between the same two reservoirs. Okay, so in other words, Carnot is going to figure out that PV diagram that gives you the most efficient cycle possible, really between two heat reservoirs. That's really between heat reservoirs. That's really Q. But probably the hour-long argument that I'm not going to do for you, you got in your textbook pretty nicely, is that Q's can be replaced by T's. And so really the two temperatures are really going to be the important thing. And that's going to be the easy things to happen to be measurable. Theorem number two. Now it's written in terms of temperatures here, right? Two heat reservoirs, that's Q. And now we'll write it in terms of temperatures. All reversible engines operating between the same two temperatures have the same efficiency. That's very interesting. No irreversible engine operating between the same two temperatures can have a greater efficiency. A reversible engine between two temperatures is the best that you can do. That does not imply 100% efficiency. That just implies the best that you can get, because it's reversible. You're not losing anything to the environment. Any real process affects the environment. So no irreversible engine can have a greater efficiency than our theoretical best, right? And that's sort of like almost like physics 101, where something is being dragged across the floor and there's just no friction, there's no sound, there's nothing. You can't do any better than that, but that's not really very realistic here. Okay, so notice that Carnot theorem number one is talking about Q energies, and theorem number two is written in terms of temperatures, something much easier to really kind of deal with here. Okay. So the mathematics is starting to come up here a little bit, but that Carnot cycle, what does that PV diagram look like? So you start at A and you're going to drive the engine around. It has to be cyclic. If you want this thing to be efficient, you got to get back to A. So A to B, you want the gas to expand to do some work for you. That's going to be an isotherm. Then B to C, it still expands, you still get more work out, but now it's an adiabatic process. You're not putting any heat in. And then from A to B and from B to C is the engine doing work. And I can see that on the diagram because from A to B and from B to C, the volume kept getting bigger. If the gas keeps getting bigger in volume, it's doing work for you. Now from C, you're going to drive it to D and then D back to A. Now you're doing work on the gas. But notice that the pressure of the gas is lower because you've already just extracted a bunch of work out. The gas is at a lower temperature, but you've got to drive it back up to that temperature, the operating temperature, to get some work out. So it's got to be cyclic if it's an efficient engine. And so what you've got is A to B is an isotherm, B to C is an adiabatic expansion, and C to D is an isothermal compression. The gas is getting driven into a smaller arena. And then D to A, you're compressing the gas because I can see the volume getting smaller. This is the Carnot cycle. So the interior of that cycle is the network done by the gas. And so he's able to show really, through, very technical mathematics and so forth, that this is the most efficient design that you can have for a cycle, for some sort of heat engine and so forth. And that's it. Okay, so we have this thing called the Carnot efficiency. The Carnot efficiency is your theoretical best efficiency that you can have if you are dealing with Q hot and Q cold. Q hot and Q cold. Here's how hot I can get it, or here's how much energy I can put in. Here's how much energy I get out of my design. Once I've got those two numbers, everything else is fixed. The best you can do is that Carnot cycle to get the highest efficiency. You can do a bunch of other stuff. It doesn't mean that they are worthless. They just won't be as efficient, but they might be easier to build and so forth. And so, in terms of manufacturing, maybe that's, the way you go and so forth. Now, the Carnot efficiency, here's the key. Up above, we were talking about efficiency in general. It had Q's in it, and you are able to show that Q is proportional to temperatures. And so the Q's can come out, the temperatures can go in, and you can work out your efficiency in terms of just temperatures. You're hot and you're cold. Your cold is the exhaust. The hot is your hot reservoir, right? You're heating up exploding gasoline and so forth. Now, when you take a look at this here, it should kind of imply immediately, units. T hot, T cold. You really don't ever want a fraction that can go to infinity. That's usually a problem. And so we're going to do this in Kelvin. Okay. And so the bottom, that is that T hot, whatever that temperature is, never really is going to be a number like 0 or anything like that at all. You really want these in Kelvin. So let's say that, for example, you get, you can get your gas up to, say, 600 K. All right. Now the exhaust is still considerably hot. Let's say that's 200 K. This tells you immediately the theoretical best efficiency that you can look for. Most real processes will be dramatically less than this. This would imply that the best you can do here would be something like 200 K divided by 600 K. That's 1/3, right? So 1 minus 1/3, this is about 0.66 or about 67% efficiency. Most real processes are about 15 or 20% of that. Okay. And so if I got something like 20%, if I used a big number, that really tells me about 13% real efficiencies. Okay. And that's probably realistic. Right? It seems like most engines are something around 15 to maybe in the low 20s or something like that. And that's it. That is the Carnot efficiency. Is kind of a theoretical best case scenario, and everything is dramatically less than that. Very, very interesting. Easy to deal with here, but I think what I would take away is this right here, this definition of the Carnot efficiency, knowing what that really means and entails, and then the Carnot cycle, right? This is really your theoretical best cycle between you're hot, and you're cold. Okay. And so once you have determined how hot you can get your gas and what the exhaust is going to be, this is the cycle that you want to have, working for you, or something very kind of close to that. Okay, so this kind of gets us through part of chapter 20. I still want to talk about this idea of entropy, and just give you some ideas, kind of how to handle that. And so you're just not walking around with this word disorganization or organization in your head, but there's a little bit more kind of substance to the whole thing here. But hopefully this kind of gets you through a little bit of this idea of reversible, irreversible processes, efficiency, and then a little bit of what Carnot actually does. So a lot of the details of the mathematics really aren't available to us at this level, but that's okay. We can understand the consequences of that work. And so, one of the consequences here is this: here is the cycle, and we want cycles to be the most efficient. And here's how we calculate the efficiency in terms of temperature, which is dramatically easier than energies and so forth. So this works out really, really kind of very nice and so forth. And so I think probably next time, in the next lecture, I'll probably have a PV diagram, and we'll go around and we'll actually find the efficiency of that cycle. And it's a long process. It's kind of like when you start looking at force problems, you go, oh, I got to do a free body diagram. And then, if you got vectors at an angle, you got to worry about the components, and you got to add them up in the x direction, you got to add them up the y direction. You might have to put those results together and add the vectors up to get a result. And it takes a while to kind of get through that. I'm going through one of these PV diagrams. It's kind of the same thing, right? You're going to start at A, you're going to go to B, you're going to go from B to C, and and so forth. And there's going to be a little bit of physics at every single part of the cycle that you just have to kind of work through. But essentially, this is energies. And so you're just doing accounting. And anytime you're doing accounting, that's what you do. Well, sometimes the energy is coming in, sometimes the energy is going out. And you got to be able to figure out, how much came in and how much went out, and then kind of keep track of that. So that's all you're really kind of doing, right? It's really kind of like doing like a checkbook, but in nature here. So we'll take a look at something like that. I think that'll probably help you out on some of this efficiency stuff here. Not terrible to do, but it just takes some time to kind of wade through that here. So hopefully this kind of gets you going in chapter 20. And I'll see you soon for chapter 20, part 2.